Hello, everybody. I am Walter Minute, and I am here in this session to talk about how to move from a prototype to a product. The idea of this presentation, as you can see in this slide, is to see what are the steps and mostly what are the hidden risks or hidden challenges that you face when you try to move from a ugly bug to a nice butterfly. That's the idea of this slide. I thought that this kind of session can be interesting in such a conference because everyone can see how many nice prototypes we have around. We look at new things on Kickstarter and everything, and then we see that not all of them really move into production. And I will try to highlight some of the challenges I discover in my experience. So if you have any issue with the audio, or you can see the slides, or you have any questions, you can use the chat to interact with me. And if you have questions, I will check the questions. Honestly, I will try, if it's something that fit in the presentation at that moment, I will try to reply immediately. Otherwise, I will have to ask you to have a bit of patience, and I will reply at the end of the presentation. So, good presenters say, okay, it's not necessary to introduce yourself when you're doing presentation, but for this one, I think I can make an exception. First, to show a nice and funny picture of myself. I'm not so nice myself, I know. And to give you my contacts, and also to talk a little bit about my background. I started my career in the 90s as a software developer. So I was developing at that time software under MS-DOS, then moved to Windows and all the new and fancy operating systems. And then at some point around 1999, I started to write embedded software. So software no longer running on PC or servers, but running on devices. And since then, this is what I've been doing for most of my time. Moving from a software development background to develop on devices also requires learning quite some things about hardware. I didn't become an hardware designer. I'm quite far from this, but I learned quite some interesting things that I would like to share with other developers. This session, it's really targeting software developers that may have to manage some hardware-related projects. It's quite a different environment. You can still apply some of the things you probably have learned developing software over the years, but you also should care about some different things, and I will try to highlight some of them in the presentation. Main point is that you can learn from your mistakes. I've been working on software for more than 20 years. And so I had many chances to make my mistakes, and hopefully I will share something I learned from them. Before talking about my mistakes, there is plenty of time for this. I will start by explaining or basically highlighting a concept that seems to be in contrast. This statement seems to contain some contrast inside it. Technology is becoming more complex and more accessible at the same time. But if you think about this, I think it's quite hard to say it's not true. We have many new devices, many new things, and many more people are using this kind of stuff. To give you an example, my mother, she's around 70 years old, and last year she started using WhatsApp and Skype. She had to do this because me and my sister were traveling around, and she needed a way to contact us and to keep in touch with us. And she learned to use this kind of new technologies. And at some point she was saying, oh, it's not that hard. It's even easier than my old telephone. I don't have to remember your number. But if you think about the technology behind this kind of services, putting many people in contact with each other, granting security, exchange this huge amount of information in real time. That's quite big and that's quite complex. So to build some stuff that people can easily use, sometimes you have to deal with complex technology. But on the other side, there is another statement that I think it's also true, and it also involves two different things, something getting more complex but more easy at the same time. Everyone can be a maker nowadays. Everyone can invest his free time into learning something new and building new devices. In this scenario, I will use the term maker just to identify people playing with hardware and software. Of course, you can be a maker also if you make something with food or something like this. But in this scenario, I will try to focus mostly on hardware and software, of course. I heard a very nice definition for this. Basically, we are democratizing hardware development. And why this is happening? First of all, because we now have low-cost evaluation boards. When I started working on embedded devices in the 90s, some evaluation boards can cost up to $10,000. I remember some evaluation board from Intel at that time, and even small companies, not just hobbyists, needed to rent those boards or try to get them for a couple of weeks for free from distributors or something like this. Putting your hands on hardware requires already quite a good investment. Nowadays, we have many devices like the Raspberry Pi, the Arduino, the Galileo, and many other devices that can really be acquired for a reasonable amount of money and that allow anyone to play with hardware and software. And also the tools we can use to write our software are getting more and more powerful. If you think about the Arduino, and I am Italian, I didn't say that at the beginning, but probably you can realize this from my accent. I am Italian, and so I'm pretty proud of the Arduino. It's one of the biggest Italian products after sport cars, food, and nice fashion. And the real revolution of the Arduino, it's really not in the hardware. It's a microcontroller, it's a very good one, but this is not something completely new. What was very new when the Arduino was released was that it was providing a free development environment that was really easy to use. You didn't have to initialize your hardware with some assembly code. Everything was already up and running. You could just download your small application, and the software was sort of hiding part of the complexity from you. You had a rich library of features, and that was really easy to use. It was also open in terms of software and hardware. That was great, and everything. And having accessible devices, having easy to use tools, helped making a community. And that was another big step compared to the past. If you were developing software on devices in the past, finding information was quite complex. You had to, most of the time, rely on the silicon vendor to get this information. Now we have lots of communities, and people can share their knowledge, and they can improve each other's projects. That's a great thing from the point of view of a developer that grew up in the pre-internet era, when most of the information was coming from printed manuals, and sharing it was quite complicated. So nowadays, even if you are thinking about devices that you couldn't even imagine like 10 years ago or 20 years ago, we have much more easier and powerful and tools to do this, and everything is much more accessible. This also creates a sort of, let's say, fight between makers and professionals. So I've been working on devices for many years, so I'm paid to write software for devices. So I think I can call myself a professional. But what's the real difference? we can have people that are, for example, professional software developers, then that turn themselves into makers when they are trying to investigate how to integrate some new devices into the solution that their company is building. I've seen many people working on software that was running on PCs and at some time deciding to remove a PC or to add a device to perform a specific function. And in that context, it made a lot of sense to use a device instead of a full PC. So we see that this difference, but many times someone can be a professional and also a maker at the same time. The idea is that the maker can bring technology into different environments. For example, we can have an archaeologist that start to play with Arduino and this kind of devices and learn how to measure temperatures, humidity, and something like this, and can collect this data to improve the way, for example, old buildings or old remainings are preserved. This is bringing some technology into different environment. And this person can be a professional and even a very well recognized professional in his own area and still work as a maker when it's related to this kind of technologies. Because nowadays experimenting is much more easier. I can just go to a website, order an Arduino for like $20, get it shipped to my house and connect some sensors and start experimenting. And if I'm stuck somewhere, I can find a community of people ready to help me. I find lots of samples and I can really understand from my mistake really quickly. And some people can point out those mistakes and help me. One interesting thing is that we can say that makers definitely can innovate. They can bring a different approach, and they can bring some technology into fields where nowadays technology probably was not so common. If we talk about computers and software. Let's change for a second our perspective. Let's talk about something completely different. You see in this picture, I took this picture in a museum that is not far from where I live, close to Milan, close to the main airport in Milan. And this is a museum of flight. And this guy is Mr. Caproni, is one of the pioneers of aviation in Italy. And they start flying not much after the Wright brothers. But if you think about the Wright brothers, they were professionals. They were quite estimated people in their field. But the point is that their field was bicycle maintenance. They were building and fixing bicycles. They just developed a great passion for flight, and so they decided to build the first airplane. And if we think that in our time, technology is evolving super quickly, just think about this. 20 years later, Lindbergh were crossing the ocean with an airplane. And in 20 years, this technology moved from just a couple of crazy people being able to detach themselves from the ground for a few hundred meters, or sorry, whatever feet, sorry for people using imperial units, to a guy that was able to cross the ocean. And by the end of the century, people take air transportation for granted. But probably at the time of when the Wright brothers were trying to fly for the first time, the most reputable professional of the time were busy inventing better ships and better trains, because those were the most common means of transportation at the time. So sometimes bringing a completely different, a fresh perspective can really change the world. Let's talk about professional. I think professional is the most abused and overrated adjective ever. If you have something you want to, let's say, make it look better or justify the fact that it's a bit more expensive, just teach professional to it. And I'm not joking, I've seen professional toilet paper in hotels. Luckily, you don't need the help of a professional to use it, and it's really an example. But on the other side, at the beginning of this presentation, I defined myself as a professional. So I really don't want to degrade the meaning of this adjective. Just change a little bit the focus. Another important topic, and I'm switching to a different thing, but you will see that later we will join back talking about professionals, is prototype versus product. So what's the difference between a prototype and a product? If we start thinking about some devices, some physical things, the first thing we need to build is a proof of concept, showing that our ideas can really work. And that's a prototype. So if you want a sort of poetic definition, prototypes are ideas trying to become real things. But we have to consider a few things. The first one is that not every prototype is going to become a product. We have many failing prototypes. And that's not bad, because people are learning through those prototypes that, for example, their idea is not really working in the real world. So they have to go back to the drawing table and think about something else, or improve their ideas. We have also to think about the fact that prototypes are living into a sort of protected environment. Everyone is caring about the prototype. We want it to work. We don't want to challenge it too much. We need to prove that it can work. We don't have to prove that it's super ruggedized and ready to withstand any kind of challenge. It should just work. But as this small bird, prototypes are small, weak, fragile, but full of promises. The important things we have to think is that our prototypes are not made to last. Probably when we are going to move in production, we are going to change quite a lot of things about our prototype. We don't need to, let's say, get too much attached to our prototype. We can change things if this is going to improve. And why we need to change something in our prototype? Most of the time, because when we designed it, when we start assembling it, we were planning to use it in the best environment possible. We were putting it on our desk. We were putting it in a way that it was not disturbed by anything. And we needed just to prove that it can work. And that's really the purpose. If you clearly state, oh, that's a prototype, that's pretty good. And it's important to state and to label something clearly as a prototype. If you don't do this, I think bad things are going to happen. If you don't tell your boss, this is a prototype, and we still need to work to make it a product, then probably you will have this guy coming to your desk every 3 days asking, oh, it's ready? I have seen it running. I mean, why we are not producing it? Oh, because it was a prototype. It's not working. It was showing that it can work. And this is also, unfortunately, what happened many times. If you look about new devices on Kickstarter, you see something running, a cool video, but sometimes I'm looking at this stuff and say, oh, those guys were really able to manage to, let's say, improve some existing technology by 10 times. That's really interesting. But then when you see that this stuff is not going to be delivered in the 6 months they promised, but it's not coming in 2 years, 3 years, and then the project disappears, then you realize that someone was not really stating the real state of his project. That was a prototype. It was probably working in some kind of protected environment, but it failed to really move to the real world. And why this happens? Because the real world is a tough place. We have devices that are not meant to run inside our office or not even inside the building. We need to have devices running outside, and we expect those devices to be working outside. But in terms of design challenges, this really changed completely the picture. If you are building your prototype, are you really thinking about the end usage, where this stuff is going to be used? Because this can really make a change, make a difference. If you think about temperature, dust, humidity, vibration, interferences, this is really something that can break your device. If you don't design it in the right way, if you have a nice prototype, for example, that helps you navigate in the traffic, avoiding traffic jams, or do something much more efficient in traffic, whatever, and you play with this stuff on your desk, simulating that you are moving by fake GPS data or something like this, as soon as you will put this stuff in your car, you will discover that it's probably not going to run. Because in cars, we have exactly this kind of challenges. We can have extreme temperatures, we have a lot of vibration, we have a lot of interferences. If you are planning to develop something that is supposed to be used inside a car, for example, knowing from the beginning all these challenges, it's really critical to really estimate the time it's going to take to have a working product. And also, when you're moving from prototype to product, you should be moving in the right direction, knowing from the beginning, okay, I use this for the prototype just because it's much faster, but I already know that this part is going to be fully redesigned when moving in production, because I know already that it's not going to work on a car. I can be completely honest with my boss, with my colleagues, with my potential investor or customers, telling them, this is what I'm doing to show it to you. I know already that that's a challenge. And probably if you already know the challenge, you can also estimate how long it's going to take, how much it's going to cost, and whatever. There are other factors you have to consider. For example, power may not be reliable, even connectivity. Connectivity probably is even worse. And so you have to design your system, hardware and software, to be able to withstand these kind of issues. You also have to think about people. For example, if you are designing a ticketing machine, think that people probably are not going to just put money and ticket inside it. They're going to do horrible things to your hardware. And you have to plan in advance if you want to have something that it's able to really perform its operation for a long time. You have, when you are designing a prototype, we said the prototype is designed to work in the best environment. When you are moving to product, you have to think about the worst case. So what are the worst situations my device can face? And this is important to have a good product. When you're thinking about the product, you also have to think about your target market. In this slide, I am doing some kind of simplification. We may have some product that actually overlap those two categories. But just to define a classification, we can have consumer and or industrial devices. What's the difference? Consumer devices are focused on price and features. Of course, when I'm trying to sell something to as many customers as I can, probably one of the most appealing point is going to be the price. So if I'm able to provide something better than the competition, what the competition is offering at a better price, then this is probably going to win on the market. And also, consumer is focused on features, and features may be functionalities, but also just design. My device must look cool and be something people really want to buy. On the other side of this slide, you see an example of an industrial product. It's a pretty big and ruggedized truck. How can you understand that this is an industrial product? Because if you go to the shop and ask, oh, in how many colors I can have this product, probably people trying to sell you a smartphone will start talking about the different colors they can have or whatever, and the guy selling you the truck will tell you, oh, what's wrong with yellow? I mean, we have been making yellow trucks for centuries. What's wrong with that? That's just to give you an idea about the different approach. This is not just an approach about selling devices, but also on the design side. One important thing you have to consider when you think if my device is consumer or is industrial. People are going to spend their money on consumer devices, but they want to make money using industrial devices. And when we think about industrial devices, for example, we think about lifetime. If you think about smartphones, people keep the same smartphone for 1 to 5 years. If you think about industrial devices, people at least plan to use the same device for 10 years because usually they invest quite a good amount of money into it and they want to get back all this money plus their own margin from it. Just think about the average age of the airplanes we use every day. Those are very expensive things that companies buy to make money. And so if they can use the same airplane for 20, 25 years, this allows them to get back the money they invested into it. We also have differences in terms of volume, so how many devices we plan to produce. And this is going to make a big difference in terms of how much our project cost will impact the final price of the device. If we are splitting this price on millions of devices, is one thing. If we are splitting this price on 1,000 devices, probably the more time we spend developing, the more our device is going to be expensive. Reliability and stability versus features are two connected points. If you think about industrial devices, having a non-working device is the worst thing that can happen, because this device is supposed to be there making money for me and it's not working, so I'm losing money. And in some industries, like food industry, if you have a machine that is processing food, like frozen food, and this machine is not working for longer than 1 or 2 hours, probably the company then has to throw away all the stuff they have in the warehouse because it has been exposed to air, it was not at the right temperature for too long. So this is not just losing money because I'm not able to sell my product to produce my thing, but also I have to throw away some additional things. So reliability for industrial devices is absolutely critical. So how can we improve our reliability, or how can we avoid mistake when we are moving from prototype to product? One point is that knowing some theory usually leads to better results. Probably you already know this guy on the right. He had quite a good theoretical background and managed to deliver a good product. Well, maybe good is really not the right adjective for the kind of product he was delivering. The idea is that, of course, you can learn from your mistakes, but it's better to avoid them in the first place, or at least know in advance which are the most challenging part of your project. Once I was playing with some sensors or devices, I don't remember, and I end up on a forum. It was the Arduino forum, looking for some people experiencing the same issues I had and looking for a solution. And at some point in one thread, there was a very funny statement from someone that was saying, "Oh, I'm not an electronic person." When someone was trying to explain, "Oh, you should do this, and that to avoid interferences or to minimize the noise in your circuit," whatever, this guy said, "Oh, I'm not an electronics person." But it's like saying, "I'm not a physics person, and so I'm not pretending that I can fall." I mean, you can ignore gravity, but sooner or later it's going to happen to you. And this is the same when you design some hardware. Sooner or later, you are going to hit some issues. We are talking about physical things, and physical things have physical limits or can be influenced by other physical things. One very simple example for this is cable lamps. Later, I've seen lots of projects on different websites, makers' websites about home automation. I've seen also some challenges and these kind of things. And what really struck me from my background was that many times people were developing home automation system using a protocol that is very popular, that is named I2C. But the main point is that I2C is a protocol that was designed to let chips on the same board talk to each other. The most extreme application of I2C is when your PC is detecting your display. Because over the cables, it may be VGA, HDMI, whatever, you have two lines that are I2C lines that are used to read some information about your display. And this is already a sort of extreme application of I2C because the cable length is quite influencing the behavior of this bus. So if you have very long cables, maybe it happened to you, you connected a projector and it was not recognized. That's exactly this issue. The cable was too long. It was not physically possible to do this because I2C was not designed for this. It has no way to check that the data is correct or something like this. And so it's not the right protocol if you want to connect distant devices. If you have some experience, and honestly, I think I do, and as I said, I got this experience from mistakes I made in the past. If you look at the project that says, oh, I'm going to do home automation, I'm going to use I2C. What? It's not possible. Or, yeah, it may be possible because you can translate I2C on differential pairs, like, for example, the Ethernet cables we are using. But of course, this involves additional hardware on each and every device you plan to connect. And if you're using I2C in the first place, probably it's because you want to use very simple devices that are very cheap. So you are going to add additional cost on top of your solution. It may work if you just plan to automate your house. Maybe you can choose better protocols. Anyway, it's not really a good solution if you really want to move this stuff in production. And there was questions about the slide. Oh, okay, it was already been answered, but anyway, just for everyone, the slides are going to be available as soon as the replay is going to be published. But I put also my contacts at the beginning, so if you have any additional question or something that you see is missing from the slides, just drop me an email or reach me on Twitter, and I will try to provide all the information you need. So, since we are facing many challenges when we plan to move our prototype into production, this is where professionals can help. We have a great idea, we implemented a wonderful prototype, now we need to move it to production. This is usually where you should think about having some, let's say, professional people involved, because they can really prevent some kind of issues. Building a physical device is really different from shipping some software. It's really not pushing a button, deploying the new version. That's a great thing about software. I love it, but it's not happening with physical devices. With physical devices, you have to get all the parts you need to build your device. And if you have a third party assembling your device, this is what commonly happens. This third party assigns slots. So you have 3 days for producing thousands of copies of your device. And your device is made of hundreds of different pieces. If one of those pieces is not there the day you are supposed to start production, then you will have still to pay for the slot, but you don't produce anything. So this is horrible from a business point of view. And probably getting people that already used to manage these kind of things in your project is a good idea. When we are talking about devices and hardware, mistakes can be really expensive. I'm not talking about this kind of mistakes, so hitting some rocks just because you want to pass too close to an island, but the end result can be like this: a huge mess, a huge disaster. It's not easy to fix hardware. Doing a hardware redesign can be horribly expensive. If you have your first prototype and then you have some like PCB manufactured, if you make a mistake, having a new cycle, so having a new PCB manufactured with all the components can take months. So it can be expensive because producing a new PCB and assembling it can be quite expensive and can also delay your project of a crazy amount of time. And usually the way it works is that if you wanted something produced very quickly, you have to pay a crazy amount of money. So if you start planning in advance about this, it's much, much better. And if you reduce the number of cycles of hardware design, definitely this is going to be much beneficial to your project. What's the way you have to do this? It's just, prevent mistakes. It's not easy in software. We have many techniques, but honestly, I think no software developer can say, oh, I never shipped a application, a program, or whatever without any bug. With hardware, this means doing many reviews. And having different people looking at the project with a fresh mind and so on can really prevent you from wasting your money in redesigns. Another point is you should decide what you want to build and want to buy. On this point, I can be pretty partial because I work for a company that is named Toradex. It's a Swiss company, and it makes computer models. So, of course, working in such a company, my suggestion is buy computer models because this is what we do. And if I don't think that this is the right way, I'm not going to work for this company. But you should really think about this. Toradex started to build computer models more than 10 years ago, but now also many silicon vendors like Intel itself are releasing their products in this format. So we have a small computer with the CPU, memory, and storage, and we can plug it in a custom carrier board that we can design to provide the custom features we need. The main advantage of this approach is that you can build on some solid ground. Someone else already solved the most complicated part of the circuits. And what you have to design as the carrier board is usually much more simpler to do and requires less testing and less iteration design to fix the issue. The point is you can save time versus save money because, of course, who's selling you a module has his own margin. Even if this can be offset by the numbers, because of course, if you're making 1,000 devices and who's making the modules is making 1 million modules, the prices of the components they get is much better than what you can get. So this can sort of set the difference in terms of cost. You need to find the right balance. Depends on your device. You should consider how much should I build, how much can I buy. And I think this slide reply to the question is say, are there product 3D SOM, so system of modules available, aside from Toradex, including certifications such as UI, CFC, etc. Usually no, and I say no, because usually the certification apply to the whole device. And certification is an important point in this slide, so you don't have to break the law. Depending on which kind of device you are making, you can have different requirements for certification. But like if you're making a device that interacts with the human body, you may have to do some medical certifications. Or if it's something used in transportation, automotive certification. And those certifications can involve hardware and software. One point can be who's providing you the building blocks of your system can tell you, okay, our system has been tested. It's matching, for example, in terms of radio frequency emission, the requirement of these standards. So you don't have to test it again, but the testing, when you're talking about certifying a device, is for the device as a whole. So even if you build a device using 10 different components that are all certified, you still need to do a full certification of your device. Using, let's say, pre-certified or anyway devices that match the requirements is still useful because your certification procedure is going to be easier, but you can take for granted that since I've been using this component, my device is okay. Because something you can add around them can change their behavior. That's the main point. So exactly, if we are talking about Wi-Fi, Zigbee, Bluetooth, whatever it's emitting, radio frequency, probably you have to do some certification, and the certification is for the whole device. Unless you provide the radio part as a sort of plug-in. So if the user is going to buy the radio part separately, then probably if that part is available on the market, it's certified, then your device is sort of excluded from this. But certification and liability, it's another important point you have to consider when building a device, because of course this can cost you money. And if you don't match the certification requirement, you may not even be able to reach your target market, and that's completely destroying your project. Okay, I managed to fit inside the 40 minutes just by a few seconds, but if anyone has questions, you can type them in the chat right now, or you can follow up later using email, Twitter, or I think I still have some slots available later for having a chat directly. Thank you very much for your time, and I hope that this presentation was interesting and useful. Oh, yes, I will go back to my contact information quickly. This means exposing you again to a picture of myself. Sorry for this, but you can copy the contact information. So you can find me on Twitter as vminute, or it's walter.minute@gmail.com. My family name, Minute, is spelled like minute in English. I don't have a mailing list. You can reach me by email at this email address. Okay. Thank you very much for your time, and I will leave this session open for a couple of minutes more. If someone else has questions, just feel free to type them in the chat. Okay, thank you again, and really don't feel shy about using my contacts. I really like to talk with people about this subject. If it was not this way, I wouldn't have done such a presentation. And if you are thinking about the device, thinking about challenges, and looking for someone to talk about this and maybe get some advice, just feel free to contact me. Thank you very much for your time, and I hope that this was useful.